Hey, what's up, guys? So in this video, previous video that I just showed that basically the goal is we want to prove this golden thompson inequality. So it's basically if A, B are basically complex Hermitian matrices, and we are showing that we want to show then that the trace of exponential A plus B is the same as is less or equal to trace of exponential A less or equal to times exponential B. Okay. And what we in the previous video that in order to prove it, what I introduced is this shatter norm. So this shatter norm for even number p basically is a to the AP norm, basically trace of a and dagger p divided by 2 over p. And so for example, a2 is just trace a squared half if you consider Hermitian. And we know this is Frobenius inner product. And obviously that we have this kind of inequality. This is basically Cauchy-Schwarz. And in the previous video that I just tell you that we can show that if there's I define this Holder inequality. If you have a1 up to AP, where p is a power of 2, then we always have trace of a1 to AP. The absolute value is less or equal to a1 p norm, a2 p norm, up to AP p norm, the product of this. And what I claim is that this Holder inequality implies a golden thompson inequality. So this is basically the previous video. And the proof is very simple, just that all the A1, A2 up to A3 up to AP to be A times B. So you have trace of AB to a power P, basically that's equal to AB P P norm. Okay, to a power P. And easy to see that AB to 2 will be just trace of AB this, so you get this. Notice that everything is Hermitian. And if you do 4, 4, you get this. Okay, so you can easily show that if you have A, B, P, P, will just be trace of A squared, B squared, P divided by 2. Okay, so you have this. Once you have this, then you know that trace AB to a P is less equal to trace A squared, B squared, and P divided by 2. And if you iterate this formula, that you can show that the trace of AB to a P is less or equal to trace of A to a P, B to a P. Okay, so this is just a very simple example. For example, if you do the AB to the fourth, which is less or equal to trace A squared, B squared using the previous formula, and you iterate, right? You use this formula again, then you prove this. Okay, so in general, that you can say that trace of A, B, P is less equal to trace of A to a P, B to a P. If P is a power of 2, and then you add A to exponential A to a P, B to exponential B to a P, then you get left hand side. And you get this, right? So now you just take P to the infinite. So the left hand side will just this. And this is famous the product formula that you get exponential A plus B. So if you plug in back, then you prove that trace of exponential A plus B is less or equal to trace of exponential A times exponential B. Okay, so basically this is the whole point, the previous video. So the remaining video, basically this video is the second video, which we were gonna prove that the Holder inequality. So if Holder inequality is true, then the golden thompson, right? The golden thompson inequality will be true. This is what we just showed, right? So our goal is to prove this Holder inequality. Okay, so this Holder inequality basically A1 up to AP, take trace. Right, that's equal to A1 P APP. So that's this is true for every even I think it's true for non-Hermitian matrices, but for our purpose, that's only focus on their all Hermitian, basically, just for convenience. But you can see my proof actually is going correct if you even though you don't assume this. Okay, so it's fine. Okay. Okay, so the proof idea basically is just mathematical induction. Okay. So this induction is quite cumbersome, so I will try to do it slowly and step by step, or you can pause a video and if you don't understand. Okay. So previously we have trace A1, A2, right? So basically it's bounded by this. This is trivial, basically it's just Cauchy-Schwarz. And since we are sure Hermitian, right? So basically it's A2, right? So it's fine that we prove that. And if it's non-Hermitian, you can also prove it because yeah, basically you can do in the same. Even though it's non-Hermitian, you can still prove that you can. If you replace the A2 dagger to be A2, still be true. Okay, because you can write a trace of A1, A2 dagger. Now it's bounded by A1 to normally A2 dagger. Right, and then you can obviously the A2 if you dagger and you take the norm, it's the same as the original, right? So it's the same. Okay, so we have shown that P equals to 2 is correct, right? So the goal is to prove that the next, right? So now we have the foundation. Okay, right? So let's assume. Let's assume that suppose we want to prove P is correct, right? And we are assuming that P divided by 4, P divided by F, P divided by 2, P divided by 4, P divided by 8 are all correct. So basically, we are doing the mathematical induction, but with each time is power of 2. Okay, so we assume power of 2 is correct. P is equal to 2 is correct. So for example, we want to prove that P is 4 is correct. If we have shown that P is 2 and 4 is correct, then what we are going to prove is that P is A is correct. Okay, so basically, this is just simple mathematical induction. And by the way, hope you guys subscribe to my channel. So this channel needs your subscription. Okay, so right, so we have trace A1 AP, right? So easy to prove this, right? So we can like bound it. Actually, if you don't take the absolute value, it's fine, right? Because the right hand side is positive. Also, you can use the P divided by 2 holder. Because my assume P divided by 2 is correct, right? So I can use P divided by the holder. So I can pair A1 to AP to be P to pair with P divided by 2 pair. So we get A1, A2, P, A3, A4, P, AP minus 1, AP, P. Okay, right? Hopefully it's trivial true. Okay, so we have shown that right. So this is true, and so we want to bound every sorry, this is P divided by 2. I'm stupid. Yeah. Right, so we want to use P divided by 2 holder, right? So we need to combine these guys, P divided by 2, P divided by 2, right? So if we can show A1, A2, P divided by 2 is A1 is bounded by A1, P, A2, P, then we are done. Because I can replace this term to be A1, A2, PP, and A3, A4, PP up to AP minus 1, P, and APP. Okay, so the remaining is to prove this is true. Okay, but why I claim that this is true? Since we already assume P divided by 2 holder is true. Okay, so let's work out the detail. Okay, so this is hopefully the final page that we prove. Okay, so our goal is to show A1, A2P divided by 2 is bounded by A1P, A2P. And we already assume that P divided by 2 holder is true. Non-commutative holder inequality is true. Then the rest is trivial because I just write down definition, right? It's P divided by 2. So it's trace of A1, A2, and A1, A2 dagger, P divided by 4, and so let's take P divided by 2 here. Okay, so basically it's trace of A1, A2 square A1, P divided by 4. And then for this, you need to use the cyclic property of trace. You can say that if P is equal to 4, right, you can remove this A1 square to the left-hand side, right? So you always can do this. So basically, you can obviously this will be equals to A1 square, A2 square, P divided by 4. If you write down, basically just A1 square, A2 square, A1 square, A2 square, A1 square, A2 square. And there are P divided by 4 pair. Right, so this is the mystery part. Right, so total how many terms we have? Right, we have P divided by 2 terms. So we can start from here and use Holder inequality again, right? So here is basically the trick. Use Holder again. So once you do this again, right? Basically, if you do this, then you get a1 square p divided by 4, right? And now you have like right, you have, let's see. Let me just see, right? So basically you can use Holder again, right? So you have p divided by 2 term, right? So your Holder inequality should be p divided by 2, right? Because you have p divided by 2 term, so total will have p divided by 2 term. So basically it's this. And there are how many of these terms? P divided by 4, right? So it's okay, and so right, it's basically this. And it's simple formula to check that if you do a1 square any m norm, if you square it, right, it's the same as you can pull out it. So basically it's the same as m 2m. Okay. So this is just simple identity. You can just check by your definition. Okay, so if this is true, then basically we can just change our left-hand side, right-hand side to be a1 to the p, right? So it's, notice this is p and the p2 here, right? So it's p divided by 2 and the a2 p divided by 2p. Okay, so now we can just delete this p divided by 2, right? We can just delete, notice that here, remove this, remove this, remove this. So what we have shown is that a1, a2, p divided by 2 is equal to a1p and a2p. Okay, so proof. Okay, so if this is correct, then this is correct, then we pull it back, then we finish the Holder inequality proof. Okay, so that's very simple. And then once it's true, then you easily prove that Golden-Thompson inequality is true once you prove this non-commutative Holder inequality. Okay, so this non-commutative Holder inequality and basically or basically original this Golden-Thompson inequality actually is very non-trivial to prove, right? It spent like 30 minutes to just write down every detail. And yeah, if you haven't seen the previous video, then I will post a link below and hope you guys subscribe to my channel. Thanks, bye.